Hello and welcome to another video. Today I am going to talk about overfit and underfit in Tensor-flow. I am going to explain everything with code snippets. Before we start, first, please check out my newsletter. I have posted the complete source code there. As always, the code in this example will use the tf.keras API. Learning how to deal with overfitting is important. Although it's often possible to achieve high accuracy on the training set, what you really want is to develop models that generalize well to a testing set or data they haven't seen before. The opposite of overfitting is underfitting. Underfitting occurs when there is still room for improvement on the trained data. This can happen for a number of reasons: if the model is not powerful enough, is over-regularized, or has simply not been trained long enough. This means the network has not learned the relevant patterns in the training data. If you train for too long though, the model will start to overfit and learn patterns from the training data that don't generalize to the test data. You need to strike a balance. Understanding how to train for an appropriate number of epochs, as you'll explore below, is a useful skill. To prevent overfitting, the best solution is to use more complete training data. The dataset should cover the full range of inputs that the model is expected to handle. Additional data may only be useful if it covers new and interesting cases. A model trained on more complete data will naturally generalize better. When that is no longer possible, the next best solution is to use techniques like regularization. These place constraints on the quantity and type of information your model can store. If a network can only afford to memorize a small number of patterns, the optimization process will force it to focus on the most prominent patterns, which have a better chance of generalizing well. In this notebook, you'll explore several common regularization techniques and use them to improve on a classification model. The first thing we need to do is to import the necessary packages. We are going to use the Higgs dataset. The goal of this tutorial is not to do particle physics, so don't dwell on the details of the dataset. It contains 11 million examples, each with 28 features, and a binary class label. The tf.data.experimental.csv dataset class can be used to read CSV records directly from a gzip file with no intermediate decompression step. That CSV reader class returns a list of scalars for each record. The following function repacks that list of scalars into a feature_vector label pair. Tensor-flow is most efficient when operating on large batches of data. So, instead of repacking each row individually, make a new tf.data dataset that takes batches of 10,000 examples, applies the pack_row function to each batch, and then splits the batches back up into individual records. Inspect some of the records from this new packed_ds. The features are not perfectly normalized, but this is sufficient for this tutorial. To keep this tutorial relatively short, use just the first 1,000 samples for validation, and the next 10,000 for training. The dataset.skip and dataset.take methods make this easy. At the same time, use the dataset.cache method to ensure that the loader doesn't need to reread the data from the file on each epoch. These datasets return individual examples. Use the dataset.batch method to create batches of an appropriate size for training. Before batching, also remember to use dataset.shuffle and dataset.repeat on the training set. The simplest way to prevent overfitting is to start with a small model, a model with a small number of learnable parameters, which is determined by the number of layers and the number of units per layer. In deep learning, the number of learnable parameters in a model is often referred to as the model's capacity. Intuitively, a model with more parameters will have more memorization capacity, and therefore will be able to easily learn a perfect dictionary-like mapping between training samples and their targets, a mapping without any generalization power, but this would be useless when making predictions on previously unseen data. Always keep this in mind: deep learning models tend to be good at fitting to the training data, but the real challenge is generalization, not fitting. On the other hand, if the network has limited memorization resources, it will not be able to learn the mapping as easily. To minimize its loss, it will have to learn compressed representations that have more predictive power. At the same time, if you make your model too small, it will have difficulty fitting to the training data. There is a balance between too much capacity and not enough capacity. Unfortunately, there is no magical formula to determine the right size or architecture of your model, in terms of the number of layers, or the right size for each layer. You will have to experiment using a series of different architectures. To find an appropriate model size, it's best to start with relatively few layers and parameters, then begin increasing the size of the layers or adding new layers until you see diminishing returns on the validation loss. Start with a simple model using only densely connected layers, tf.keras.layers, dense, as a baseline, then create larger models, and compare them. Many models train better if you gradually reduce the learning rate during training. Use tf.keras.optimizers.schedules to reduce the learning rate over time. The code above sets a tf.keras.optimizers.schedules.inverse time decay to hyperbolically decrease the learning rate to 1/2 of the base rate at 1000 epochs, 1/3 at 2000 epochs, and so on. Each model in this tutorial will use the same training configuration. So set these up in a reusable way, starting with the list of callbacks. The training for this tutorial runs for many short epochs. To reduce the logging noise, use the tf.epoch, which simply prints a for each epoch, and a full set of metrics every 100 epochs. Next include tf.keras.callbacks.early stopping to avoid long and unnecessary training times. Note that this callback is set to monitor the val_binary_cross entropy, not the val_loss. This difference will be important later. Use callbacks.tensorboard to generate tensorboard logs for the training. Similarly, each model will use the same model.compile and model.fit settings. Start by training a model. Now check how the model did. To check if you can beat the performance of the small model, progressively train some larger models. Try 2 hidden layers with 16 units each. The solid lines show the training loss, and the dashed lines show the validation loss. Remember, a lower validation loss indicates a better model. While building a larger model gives it more power, if this power is not constrained somehow, it can easily overfit to the training set. In this example, typically, only the tiny model manages to avoid overfitting altogether, and each of the larger models overfit the data more quickly. This becomes so severe for the large model that you need to switch the plot to a log scale to really figure out what's happening. This is apparent if you plot and compare the validation metrics to the training metrics. It's normal for there to be a small difference. If both metrics are moving in the same direction, everything is fine. If the validation metric begins to stagnate while the training metric continues to improve, you are probably close to overfitting. If the validation metric is going in the wrong direction, the model is clearly overfitting. Before getting into the content of this section, copy the training logs from the tiny model above to use as a baseline for comparison. You may be familiar with Occam's razor principle. Given 2 explanations for something, the explanation most likely to be correct is the simplest one, the one that makes the least amount of assumptions. This also applies to the models learned by neural networks. Given some training data and a network architecture, there are multiple sets of weights values, multiple models, that could explain the data, and simpler models are less likely to overfit than complex ones. A simple model, in this context, is a model where the distribution of parameter values has less entropy, or a model with fewer parameters altogether, as demonstrated in the section above. Thus, a common way to mitigate overfitting is to put constraints on the complexity of a network by forcing its weights only to take small values, which makes the distribution of weight values more regular. This is called weight regularization, and it is done by adding to the loss function of the network a cost associated with having large weights. This cost comes in 2 flavors. L1 regularization, where the cost added is proportional to the absolute value of the weights coefficients, i.e. to what is called the L1 norm of the weights. L2 regularization, where the cost added is proportional to the square of the value of the weight's coefficients, i.e. to what is called the squared L2 norm of the weights. L2 regularization is also called weight decay in the context of neural networks. Don't let the different name confuse you. Weight decay is mathematically the exact same as L2 regularization. L1 regularization pushes weights towards exactly zero, encouraging a sparse model. L2 regularization will penalize the weights parameters without making them sparse, since the penalty goes to zero for small weights, one reason why L2 is more common. In TF.Keras, weight regularization is added by passing weight regularizer instances to layers as keyword arguments. Add L2 weight regularization. L2, 0.001, means that every coefficient in the weight matrix of the layer will add 0.001 weight underscore coefficient underscore value asterisk 2 to the total loss of the network. That is why we're monitoring the binary underscore cross-entropy directly. Because it doesn't have this regularization component mixed in. So, that same large model with an L2 regularization penalty performs much better. As demonstrated in the diagram above, the L2 regularized model is now much more competitive with the tiny model. This L2 model is also much more resistant to overfitting than the large model it was based on, despite having the same number of parameters. There are two important things to note about this sort of regularization. If you are writing your own training loop, then you need to be sure to ask the model for its regularization losses. This implementation works by adding the weight penalties to the model's loss, and then applying a standard optimization procedure after that. There is a second approach that instead only runs the optimizer on the raw loss, and then while applying the calculated step the optimizer also applies some weight decay. This decoupled weight decay is used in optimizers like TF.Keras.optimizers, FTRL and TFA.optimizers.AtomW.